¿Vos la dejo?
Sí.
Thanks. Well, it's been fun. I'm kind of glad it's the last one. Work. You guys have worn me out. I guess I want to remind you that the whole point of these lectures, I think, or my plan for them, is to give a pretty, I guess low-tech is not the right word, but I don't know, some picture to a very general audience of what this stuff is all about. And I haven't gotten into detail in any, I don't know, anything close to the way I would like to, or the way other people would like me to. And that's too bad. But I hope that somehow you've gotten something out of these lectures, some understanding of what the picture is like. So today, I guess I want to follow this process of just doing a little bit of review of what we did last time. And then I'll jump into new stuff. This is going to be the stuff from the very end last time, which went by real fast anyway. So it'll be good to review it. And this is really the worst stuff of the 3 lectures. Okay, it's sort of the most technical stuff. And we're going to do it, and then we're going to kind of just remember the ideas and forget all the details. But I have a fixed ground field, and this will denote smooth schemes over my field. So I want raisable tanks, finite types, separated, whatever niceness I have to see what to throw in there. And what we were talking about last time is how to take this category and embed it into something bigger. I was calling it MV, or one other better name, or a Voevodsky category. And this is supposed to be like the category of topological spaces. So if you want, let's call the objects their monotypic spaces, the best way to think about them. And this is supposed to be a flexible enough category that we can do homotopy to. Now, I'll review the definition, but let me first review the idea, or thing to keep in your head. So if you have a topological space, then I can use that to get a functor from spaces to spaces, sending x into the space of maps from x to y. That's what that means. And let's give that a name. Let's call it R1. R is for representable function determined by y. And this has some basic properties, which I want to zero in on. One is that, well, this functor, if you put in x or you put in x across an interval, then it gives you basically the same answer. So the functor evaluated at x across an interval is evaluated at x. There's a map. And that's what you put. So the space I get as my output is the same, whether I put x there or x cross theta. So that's called homotopy invariance. Oh, it's an homotopy, yeah. I'm a homotopy theorist, so I'm going to use that all the time. So there's that. The second property is sort of a baby version of the real property I'll get to in a minute. We have a little open cover. So I'm just doing 2 full covers. So you have a space and covering by 2 open sets. Then I can write down this little square. So that's the space of all maps from x to y. There's maps from u to y, maps from b to y, you intersect b to y. There are various restriction maps like that. And this is a homotopy pullback square. What that means is that, well, for these 3 guys, I can form a homotopy pullback, a point here, a point there, a path between them here. And that matches the homotopy pullback in its equivalence. So let me write that. Yeah, exactly. Yeah, this is sort of the Uber property which leads to my Vator sequence of cohomologies. If y was an element of a plane space, then this would be telling me the homotopy groups would be homology groups. And this would give me a line exact sequence of homology languages. So this is my Voevodsky structure. Different MV than that MV. All right, and the last thing was that if I take the homotopy groups of this space, then, well, I'm looking at, so maps from SI into the function space. I can take the X and put it over here. This corresponds to SI. Well, put a smash there, don't worry about that. So what this really is homotopy classical maps from the ith extension of X to Y. SI is a string. So the values of my functor are encoding homotopy classical maps in all dimensions. Now, what I told you last time is that if you forgot about Y and just look at arbitrary functors satisfying these two properties, then they all end up coming from a space in a certain sense. And that's because the category of topological space is so nice. You can construct basically anything you want. You can construct something that represents your functor. Okay? But over here, where we don't have such a nice category, it's reasonable to use these functors instead as substitutes for spaces. So what this category is explicitly is this is the category of functors from our base category. That's going to be contravariant. This is a contravariant functor. And so some functional sets, or if you don't like that, you can take a homological space.
So, sorry.
Yeah.
Is this sort of a standard thing to do?
Yeah. Pretty much. So let me give you one example that you probably know. So Grothendieck had affine schemes. He wanted to glue them together to make all schemes, and he used functors to do it.
Right. So then why did it take him 50 years to think of that?
That's in some ways a good question. I mean, what I'm describing is very naive. It's very easy to understand. What people knew is that if you take functors into sets, that's like formally adding colimits into your category. What we want to do is add a homotopy theory as well, so that's where the simplicial direction goes.
So the clever thing was the adding this category of functors was the target that had, and the target of that was missing. I'm just saying, why did Grothendieck think of this when you're saying all this is kind of natural to you guys?
I don't know. Eric, do you have anything you can say about that? Yeah. So in this description, so this is the basic category. Then there's some non-trivial stuff that goes into defining homotopy classes of maps. These are just the objects. And Grothendieck really was not a homotopy theorist. And our techniques for homotopy theory have developed a lot in the last 30 years or so. So to me, that's really the advance. And again, it's still very formal, but 30 years ago they didn't have those formal techniques at their disposal. All right. So, yeah, so those are the objects. And then recall that we said a functor is space-like. Two basic things you need to know. The other satisfies the analogs of these two properties. I don't have an interval anymore because I'm with algebraic geometry, so I'm going to replace that by that. But other than that, things remain the same. Although it's risky open covers here for now. And the second thing was given any functor, then you can make it space-like by doing some complicated process to it. Like in a universal way. So this is this complicated thing where we took our functor and we did something to it to force property 1, then we did something to it to force property 2. It's like unification. Now property 1 is destroyed, so we go back and do it again. And continue forever and get this new thing out of that. once you do that, then you define homotopy classes of maps in this category. So the maps from sigma I of x into a given functor is just pi I. Well, you take your Harmonic replacement, you evaluate x, it'll take its homotopy. So that's coming from the analog here. So now this thing, here's the formal definition of these as much as I'm willing to go through. And there are a couple of things I want to say about it. So if it weren't for that second property, if it weren't for the sheafification part, then it would be pretty much what it was pretty close to what you're used to, taking maps into F and then making a homotopy invariant by lining up by homotopy. It's that second Maya-View-Torres property which causes some complication. I just want to convince you that that's kind of important. So what I told you is that what ends up happening in this theory is that, well, if you take some kind of infinite Grassmannian, the suspensions for a minute. This ends up being algebraic Q-knowledge. So that's a theory. It's not especially hard theory, but it turns out that way. And now, why does this work in ordinary topology? So, in topology, if you have a vector bundle over a space X, then of course it's classified by mapping to a Grassmannian. So, let's do a complex vector. So there's some Grassmannian, some map like that. Here's the universal tautological bundle. And this is pulled back. So any vector bundle can be pulled back from one of these tautological bundles. And so that sort of gives you the correspondence here. Given a vector bundle, you have a map into a Grassmannian. It's one direction. In algebraic geometry, this is not true anymore. Tautological vector bundles over Grassmannians all come with embeddings into a trivial bundle. That's K with an underline. So the only vector bundles I can get by pulling back along an algebraic map are things which have an embedding in a trivial bundle. Well, there are lots of them that don't have that. So you can't just take maps from X into your objects and divide by homotopies. You have to somehow add more maps from somewhere. And the way we're doing that is by breaking up X into small pieces and picking up the maps from the individual pieces. Patching into homotopy. So I probably won't get this right. I think if X is affine, then this is okay. I think that any, so a vector bundle over an affine thing can be embedded in some numbers. So you cover your scheme by affines, pick up the maps there, and then patch. Okay. So what do I want to say next? That was the beginning. Now, let me give you a little aside on homotopy covalence. I'm going to be needing this. So I'll just give you some basic pictures. Suppose I have a space X, space Y, and a space A, which somehow maps into it. Then the covariance of this diagram, you know, of course. You take X and Y, and you identify the images of A. So this is I, this is J. Then you make I of A. J of A. Take some kind of quotient function. Not, no. So this is the colimit. Again, it's probably the easiest for people to think about the case more super. That certainly is always the colimit. For the homotopy colimit, we'll spell. What we're going to do is instead of making the identifications on the nose, we're going to make them up to homotopy. So I'm going to take X, I'm going to take Y, I'm going to take A, cross it with a cylinder. Here. And then I'm going to glue the image on. That's the homotopy. There's an obvious map, this way, where I sort of take this fattened homotopy and I just collapse it all to a point and make that implications on the nodes. So you should think of the homotopy column as a fattened up version of the column, which behaves better than the homotopy. Just some basic examples that you know. If I have an inclusion of spaces, let's put a point there. The colimit would be just the motion. The homotopy colimit is the mapping colimit. Take the cylinder on A, move one end into X, move the other into a point. So that gives you a colimit. Another example, I have this diagram. And what's the homotopy colimit? Well, I take X, cross it with an interval, that's a cylinder, move the two ends to a point, so I get this expression. Get X with two homotopy. These are easy examples because I'm really only adding in one homotopy. It can get much worse. One other case you might have seen. Suppose I have a space with a group action on it. So that's a little diagram. One object, a bunch of maps corresponding to the group elements. The colimit are orbits, x1g. The homotopy colimit. What's that? No. There are lots of maps. So I have one map for every element of the group. My diagram looks like this. I have a lot of them. See that?
Is this for only finite groups?
No, it's going to work for anything. It's just the definition. The homotopy colimit is the row construction. So this EG, if you haven't seen this, don't worry about it. But EG is some big contractible space, which is encoding all the extra homotopies you have to put in to make the homotopy colimit as opposed to a colimit. Now, the most basic fact I need about this is that if you have an open cover, space X. So now I'm not just using two-fold open covers, anything you want. Then you can form the following diagram. It's huge, it's a check diagram. So take all the opens, take all the intersections, all the triple intersections. There's a bunch of maps between these things. Go all the way up. The homotopy colimit of that huge diagram turns out to be the same to the homotopy of X itself. So if it was ordinary colimit, that would be obvious. This higher stuff doesn't matter. I take all the opens, I glue them along the intersections, I get my space. The fact that the homotopy colimit works, you need all this extra data, and there's a little bit something to prove there. It's not especially hard. Well, let me give you one little example. This is the basis for why things like check homology work. Let's take this one. So I'm going to cover it by a U, a V. And then U intersect V is two pieces like that. So now I'm going to come into my picture there. So now I'm going to make the little diagram. I have that. Okay, but the homotopy colimit of this is this one again. Let's see if this is reasonable. U intersect V was that. So that's really S naught. It's 2 points up to homotopy. U is contractible. V is contractible. And I just told you that when you take the homotopy colimit of a diagram like that, you get the suspension. The suspension of S naught is S1. the moral is that a space can be homotopically decomposed in terms of pieces of a cover. Now, the reason I want this is that these two are somewhat different description of the homotopy theory of this category NP. Yeah, it's not that different, but somehow it encapsulates the things that you use in practice when you're playing around with this. So the homotopy theory of this funny category that we've made, basically what it is you get it by, first of all, you formally add all homotopy colimits for diagrams and schemes. If you formally added colimits, it would be species of sets. Formally adding homotopy colimits turns out to be species of special sets. And then you want to impose two relations into your homotopy theory. First is that x cross A1 should be the same as x homotopy. The second is if you have a cover, then the homotopy colimit of that check diagram should be the same as your space mix. So you enforce these two properties. This description can be made completely precise, but it's not worth doing it here.
I thought B was asserted over there.
This is for our topological spaces. So it's always true for topological spaces. Now I'm building a homotopy for schemes in which I force that feature. I'm trying to describe this homotopy theory for schemes as a universal construction. You do the most general thing possible by formally adding homotopy colimits, and then force these two properties, which hold for topological spaces, to be true here as well.
So how does that fail in providing? I mean, is your
These are now
outgoing varieties, or you're saying for all coverings?
I'm saying for all zero-density coverings, but I think the point is that you don't, if you just work in the category of varieties, you can't make sense of these statements. Right? You don't know what a homotopy colimit of varieties is. You do if you go into spacers, but not here. So what we're doing is we're building a homotopy theory of varieties, and we're forcing these two statements to be true. Forcing. All this is a translation of those properties I wrote down about space-like functors. This corresponds to the homotopy invariance for space-like functors. This corresponds to that distant property. Just saying it in a different way.
I guess I didn't understand the definition.
So homotopy colimits are things that should exist in any homotopy theory. Okay, I told you what they are for spaces. I'm asking you to imagine a homotopy theory for schemes in which you have the same kind of properties. Okay. I'm just asking you to imagine. You're back in grade school.
This is sort of a psychological question.
Yes and no. As I said, this can be made completely precise. I'm just not giving you the details. There is a theorem which says this is equal to this. But to give the details would be a long detour through category. And I don't want to do it.
Can I ask the same question another way?
Yeah.
Are you saying that you need to do more work, or that by the time you made your definition, this has already been built?
So if I take that old definition in terms of functors, I'm saying that turns out to be exactly equivalent to this. Okay, so these things are built into the theory. And you can even, if you go back and look at those properties I wrote down as space-like functors, it is a translation of these two properties. The reason I wanted to write it like this is because these are the things you need in practice. So let's do some sample manipulations. to just be working in this category. We're going to forget all machinery and just play around. So, I'm doing this because I need some of the details later, so they weren't treated late. But there's A1. Okay, let's do this. That's the version. Put it in 0 and 1. Here's another copy of A1. Yeah. Those two things. I could form the homotopy colon of that diagram. So what that is 0, 1. So that's a geometric object. There's another geometric object. And they've been glued together with lines which are not geometric anymore. These are topological lines, if you like. The homotopies you use, if you like, when gluing things together, are coming from this formal aspect. So that's a picture of what this object is going to look like in our category. In practice, I won't draw those lines. I'll just write it like that. I'm going to remember that when things are glued together like this, secretly there are homotopies. So I can do geometry along this line. I can do geometry along that line, but I can't sort of cross over. Okay. So here are my atoms, and here is the glue coming from topology. So this gives me an object in my category, which is sort of like a sphere. Okay, if you sort of forget the fact that things are going to infinity, it looks like S1. So I'm going to call it S10.
So in the algebraic geometry line, are those actually embedded points in some sense, or
what do you mean by embedded points?
in terms of the scheme structure?
All I mean is that there are points on the scheme.
There's no special structure going on.
No special structure. The reason for the bigrading here is that you have another kind of circle, which is A1 minus 0. So now I'm going to draw it like this. So if you think, you should always think in terms of the complex picture, even though when I'm saying works over any view. So over the complex numbers, this looks like a plane minus the origin. So topologically, it's a circle. But the geometry going on is very different from the geometry going on in this object. So this is another kind of circle. We're going to call S11. And now we have things where we can build off from these guys. So here's a definition for you. Topology, we have a smash product. I'm going to define the same thing in this category. What you do is you take the ordinary product and you take the homotopy quotient, where you kill x across the point and y across the y. So these are supposed to be pointed spaces. So in topology, these things are just sitting inside very conclusions. You can just collapse them to a point. But whenever I write a quotient like this, I really mean a homotopy quotient. So the reason I need this operation is it gives you a way of building big spheres into small spheres. So let's go back to topology just for a minute and do S1, smash S1. So to get that, I'm supposed to take the product. So for me, S1 is going to be that. Line with 2 points identified. If I take the product, then I get this. A torus. And now I'm supposed to collapse things. So I'm going to take one of the circles and collapse them. Collapse that circle. And then we're going to take this other circle and collapse it. Well, this purple circle is the same as that one. This orange circle is the same as that one, because it's been identified. So we have a disk where we collapse the boundary. So this is S2. And generally, Sn smash Sn. Sn plus N. So probably only one. Decide about that. So now that I have these two basic spheres, I can define a whole family. P vert equal to Q, then SPQ, you're going to get by doing S10 smash with itself P minus Q times. And smash with S11 Q times.
So what's the object you got to take VA points and sort of identify and mark each with 2 points. And
So you mean this picture?
I guess I can.
Okay, this turns out to be equivalent to an S1. So it's really the same thing as that. What you could also do is go in here, side A3, and take the coordinate hyperplanes together with the one which kind of cuts it like that. So the plane x minus 1 minus b. Oops. So I have 4 sides, sort of fits together to form a tetrahedron. If I do things like that, I'm going to get S2. Anytime you take contractible things and glue them together in a formal way, you get something which has purely topological aspect. So, to explain these indices, this is called, well, this is basically the topological dimension of your object. And this guy is called the weight. And somehow reflects the geometry of what's going on. So if I take a bunch of A2s, which are contractible, glue them together, there's not much interesting geometry there in that object. So that's why that's 0. This guy had a lot of geometry in it. There's 1 topological. So I want to show you that if I take P1, that's like a sphere, topologically. I want to convince you that it should be called S21 in this one. So, well, it's a picture I just erased. There's P1. I can cover it by these pieces, U and B. And U intersect B. U is a copy of A1. B is a copy of A1. This is an open cover. They're glued together along A1 minus 0, that's their intersection. And the homotopy pushout is P1, using this relation. So I've built this back into my theory, that P1 can be obtained as the homotopy coordinate of that diagram. Now I'm going to change the diagram onto homotopy. These A1s are contractible. A1 minus 0 by definition was S11. And what I told you is that when you do the homotopy coordinate or something like that, you get the suspension. Suspension in our category is just doing topological stuff. So it's only going to increase that first index. Okay, that's 2. Let's do one more of these. A2 minus lowered. So looking at my picture, unfortunately, it looks the same as over there. It'll be something different. Here's an A1. Topologically, this is a sphere. So this should be S3 something. We need to figure out what the something is. So I'm going to do the following. I'm going to take an open cover in a certain way. So one piece is where I remove that line. A1 cross A1 minus 0. The other piece will be where I remove the other line.
And everything you're doing now is over C, right?
No. So I'm using C to motivate the pictures, but these little computations, if that's what you want to call them, will work over any field.
So seeing that the punctured affine line is topologically a circle You're claiming is true for any table?
Well, I'm saying, so in order to understand the topology part of it, you think over C to get your intuition right. Okay? But the indices, we're going to work out the same over any field.
Okay.
One way to think about it, maybe, so here's something you can say. Suppose I was working over a finite field. Okay? Then to any scheme, you can attach a kind of a tau homotopy type. And this thing is going to give me a kind of circle, even over any field. So there is this intrinsic topological dimension, even if you don't have any intrinsic topology there.
I was more worried about R.
There are.
So you're doing algebraic closed at least or not?
So, well, let me think first of that. These are definitions, yeah. But I want to think of what I can say to happier. That's how much we type of A1 minus that. Right. Yeah, you're right. You're right. Okay. I feel like there's a little bit more intuition there, but I think you're right. We should just take it as definition. All right, so I'm going back to this example. I'm defining an open cover point. So this is where I remove the vertical line, the vertical axis, the horizontal axis. The intersection is this. And by this relation again, the homotopy push out is my space. Now again, let's modify things up to homotopy. We can get rid of the A1s. So if I rewrite this diagram, S11 cross S1. I get rid of that because it's contractible. This is the second projection. I get rid of this A1 because it's contractible. And the first projection. Taking the homotopy colimiter. So now I'm going to just pull something out of my hat. Whenever you have a product, take the two projections. It's a fact that works in any homotopy theory. What you get is the suspension of the smash product. That's not hard to prove, but I don't want to go really deep. Just silly manipulations. Or these functions. So that would give me S22. I bump up the topological dimension. Get S6. So these are supposed to be basic, very basic examples of using these two relations to understand how a certain algebraic variety homotopy decomposes in terms of other things. In terms of these basic circles in this case. All right. So this bigrading on the spheres passes to everything inside of your homotopy theory. Homotopy groups of spheres are bigraded, cohomology theories are bigraded, everything ends up being bigraded. This is going to do very badly on time. 20 minutes. Let me just write one more thing down, which is fun. This is algebraic Voevodsky. So in topology, if you take C cross VU, you do two of it, and you get C cross VU. And our new homotopy theory of C's, you take Z cross VGL. So you take the infinite general linear group, form a classifying space in the usual way. Get some object here. If you do loop 2, 0 of that, well, that's something complicated. So it's looking like it's not Bott periodic. But if you do loop 2, 1 of it, then you get the same thing. So this means match from S21 into my object. And this is really not so surprising after you see it. S21 was P1. This says something about how bundles on X cross P1 relate to bundles on X. And that's really what the upgrade is about. All right. Now, what I wanted to do to close off this material, let me say this. So now I've sort of made for you this homotopy theory of schemes, described it in a couple of ways, in the universal construction. Inside there, we wanted the abelian group objects would somehow be the motives. And part of understanding what happened with motives was to understand what happened when you map from one motive to another. These were some kind of cohomology groups. Some kind of singular cohomology groups. I want to say something about how you make this category work in it. So the naive thing would be to say, all right, before we use functors into simplicial sets. And that was all spaces. If we want the abelian ones, let's go into the abelian objects here, which are just chain complexes. So you would use functors like that to impose the same space-like relations. With the whole theory. So this will be your first guess. All you want to do is take the same idea and make it abelian. You replace simplicial sets by chain complexes. This is a little bit too naive. So let me tell you how to fix it. So the machinery for fixing it goes under the pre-sheaf of transfers. And this is all Voevodsky's work, or most of it. Much of the basic stuff that I'm describing. Some of the later stuff will be redone in Voevodsky. But this was a big advance. This is what has sort of let people get their hands on much of the cohomology proof theorems about it. There's definitely a lot of stuff going on which is not trivial. I'm only going to give you the idea, so I'm not going to be doing the interesting stuff. All right. So first we'll do the idea from topology, and then I'll translate that and actually give you some definitions. So suppose I have a map of spaces. You want to think about what motives look like in topology. So remember the motive of a space was the free-varying group on it. And of course it's a functor, so I get an inducement. If this was a branch cover, then it turns out you also get a map coming back, cover transfer map. So let me draw some pictures which will tell you what I mean by this and how to get this map. It's very easy to understand. So let's take that for my base. And my cover, let's make it look something like that. So it's almost a covering space where you have certain places where it changes. So if I take the free-varying group on X, the free-varying group on this thing, I have to describe the map back. So I can just take a generator and a point and tell you where it goes, and we'll extend linearly. Given a point here, x, middle x, then I take all its pre-images. So let's call those E1, E2, E3. And now I send it to the formal solid. Like that. I can do this because I've taken the free-varying group. If I took, let's say, this to be my point, well, now I only have two guys. F2. But this guy really has multiplicity 2. So y would go to 2 times F1. Very easy not to describe. So in topology, our motives come with transfer maps or branch covers. What happens is that when we make this category of geometric windows, we have to force those into the picture. But that's it. So, I guess let me say one more thing about the functorial perspective. I'm going to rewrite this in slightly a different way. Suppose I have a mode of M, topological invariant group, and now I start looking at maps into it. So I'm going back to these functors. Maps into M. Let's just do long, actually. So X, Z goes to Z, the set of maps. What I'm saying is that if I have a map from my branch cover into M, then I can extend it over X, like that. So given a point here, I lift it into the fiber, find out where those fiber points go, and add them up. So if I have a branch cover, then when I look at the functions, I get a transfer map going down. If I have a map from my branch cover into M, I can extend it over X. Well, extend is the wrong word. Get a map from X. So here's a definition for you. Now I'm going back to geometry. A tree sheaf with transfers. So it's going to be a functor from smooth schemes into chain complexes. This is the naive thing. And now we have to add in these transfer maps. And now we come to this funny point. There are different ways you can talk about branch covers in algebraic geometry. And if you read these Voevodsky papers, he's constantly changing his mind a little bit about which way he wants to do it. Now, I'm actually not an expert. I don't know which way ends up being the right one. They're all pretty similar. So I'm going to describe one of them. So here we go. For every smooth scheme X and every curve over X. So a scheme over X, which is one-dimensional. This is all supposed to be smooth, and so on. And every cycle finite and surjective over X. So for all that data, we're going to get certain transfer maps. Let me draw the picture. So here's my X. Here's the curve over X. These are one-dimensional fibers. So given a cycle on this curve, which is finite and surjective over X, well, that means it's something like a branch cover. It's a branch cover which is sitting inside of C. We're going to call that C. So anytime you have this data, you need a transfer map. Which I'll call phi Z. Going from the value of the functor on C down to the value on X. So your picture should be that if I had a map from C into my motive, I can pull it back to the branch cover. Then using that kind of technique, I can extend it down over X. Extend is still the wrong word. But once I have it defined on the branch cover, I get a transfer map down to X. And that's what this is. And that has to satisfy basic properties. The basic properties are really real easy if you understand this topological picture. Okay? They're just very natural things to want to. So I won't write them down, especially since I'm almost out of time. It's been very quiet. anytime you have a functor on a category, that's a free sheet. So usually, I guess, you would talk about free sheets of sets or a Boolean group or something like that. This is free sheets of complex. Just nonsense terminology. All right, so this thing which I've been writing this, these are subsets or category of motives. These are going to be free sheets of transfers. This is the category of free sheets of transfers. And remember, this is a place where we're doing homotopy here. So, in the end, we really want to calculate homotopy values from maps. Objects. And I'm going to get that kind of thing using the old method. Let's make this X. So I take my pre-sheet, make a homotopy invariant, sheetify it in this complicated way, make a homotopy invariant again, blah, blah, blah. And now theorem. That actually, the method is not so complicated. For a pre-sheet of transfers, this complicated method degenerates after 2 steps. So if I want to calculate something like that, remember X is sort of the image in my category, so it's really the motive. I'm not writing it that way yet. But, so I would take my thing, make a homotopy invariant. I would sheetify it homotopically. Now, since we're dealing with complex and invariant groups, this really is hypercohomology. And now I would evaluate an X and take either the ith homotopy group if you like, but it's abelian. So let's read it out. So this very, very complicated process to generate. You can actually get your hands on it. Now, I only have one thing left to do. Take me maybe a little bit over 5 minutes, but not much. So I want to describe what kind of things you should stick into that spot, which are reasonable. So again, I'll start out with just the basic idea. Here we'll have topological motives. Here we'll have geometric motives. Say that again?
What is that?
F is one of your functors here. So it's sort of one of the objects in this category. You're trying to calculate how much the concept maps into it. So you take your functor and do this stuff. I'm about to tell you what kind of functors you would want to use, which might be better. Feels like I lost you somewhere. But ask another question. Or... So it's actually not so bad. So really what's going to happen for us is that F will be appreciative of abelian groups. So that's not too bad. So seeing F, evaluated X, what you do is, it's like the construction of Bloch-Hierarchical groups. You take F of X, you take F of X cross A1. If you have a couple maps down, you take F of X cross A2, 3 maps down, you take some kind of geometric realization. That's what C. So you're making things homotopy invariant in the same way that Bloch took the Chow group and sort of extended them up to. It's a pretty concrete thing. It's going to be, well, so, yeah. What's the best way to say it? Realization means total complex in the Boolean world. So you take a bunch of chain complexes. This is really now a double complex. I'll take the total. So realization brings you back down into whatever world you started. You started out with chain complexes, whatever those were. Then you end up with a chain complex. Well, so this was some kind of sheafification process. And the way you sheafify a pre-sheaf of chain complexes is you do hypercohomology. That's the right way to sheafify it. So before, we were dealing with simplicial sets, which was some complicated thing which I didn't quite describe to you. But here, for pre-sheaf of chain compasses of invariant groups it really is. Other questions at this point? Okay, I'm down on time, 5 minutes, and then I'll stop. So let's go through our picture again. So the topological model of the space was organization. That corresponds to something here. You can also form, if you have a space, you can take this one-point compactification, construct a reduced invariant group where infinity is made to be 0. That's going to correspond to something which is like the mode of complex mode. So cycles, as they move out to infinity, they're getting closer to the 0 element. So they're going away. These things are really 0 cycles. You could also try to define a space of R cycles. And no one's really bothered to do that in the topological world because it doesn't give you something very interesting. It's going to end up giving you loose R on 0 cycles. So on-grid does something like this in the case of analytic cycles and analytic space. But all you've done is taken, if you think about the homotopy groups, then this has the homology groups of X and this is homotopy group. I'm just going to shift them down R swaps. But the space of R cycles should give you something over here. It's going to be the motive of R cycle. And now the connection is not so easy. The reason I did all that stuff with spheres is because I wanted to write down this relation. And if I take VR plus 1, I take VR of X, as a space, that's going to be the same as loop 2RR. So the naive topological loops become these more geometric loops. All right, so these are things which would be motives. I should be able to write down functors corresponding to them. So let me just do that and stop. So given a scheme Y, I'm going to write down functors which somehow correspond to the space of R cycles on Y and the space of R cycles on the one-point compactification of Y. And that's going to be the analog. So these are going to be functors from smooth schemes into invariant groups. So given a smooth scheme X, I'll tell you what we're going to send it to. And what you're supposed to do is think of, okay, if I had this object, what would it be like to map X into it? So for any point of X, I have an R cycle. So I can draw this picture. There's X. There's Y. Let's put the other one in. For any point of X, I have an R cycle on Y. So if I put them all together, I have a cycle on X cross Y, which is dimension R and the fibers over X. So I'm going to send that to the Fourier-Baron group. Cycles on X cross Y, which are equidimensional. This is Zy, so I actually want equidimensional and proper. Over X. Again, I may be leaving out some technical involvement here. I probably am. But this is more or less what it is. This is going to be the same thing, except I dropped the proper.